In the last week, we explored the Cauchy-Riemann equations. The Cauchy-Riemann equations were the right set of conditions which ensured that differentiable function also turned out to be complex differentiable. Given a holomorphic function, the Cauchy-Riemann equation tied the real part of the holomorphic function with the imaginary part of the holomorphic function. We begin this week by observing that the Cauchy-Riemann equation imparts an extra set of condition on these functions, the real part and the imaginary part of a given holomorphic function, which is captured by the more common harmonic functions. So let's start. In this lecture, we will always assume that our holomorphic functions are twice continuously differentiable. So I would like to note that this is a redundant condition. I say that it is redundant because holomorphic functions will always satisfy this criterion. We will prove that later, but since we have not proved it yet, let me just put this extra condition. Let me just note that this is a redundant condition. And let's also recall that given a holomorphic function, so let f from say u to c be a holomorphic function, then what does the Cauchy-Riemann equation says? The Cauchy-Riemann equation tells us that if f is u plus iv, then dou u by dou x is equal to at every point z. So we have assumed that it is holomorphic and hence complex differentiable at every point on u. So dou u by dou x at z is the same as dou v by dou y of z, and dou u by dou y of z is equal to minus of dou u by dou v by dou x of z. Now, if we take we have assumed that f is twice differentiable, so we can take the next derivative. For example, we can look at the second order partial derivative of u. So from star, we get, let's see what happens to dou square u by dou x square of z. This is going to be equal to dou square u by dou x dou y of z. And what happens to dou square u by dou y square? This is going to be equal to minus of dou square v by dou x, dou y dou x rather, of z. Now, if we invoke the calculus that we have studied earlier, or a course on real analysis in several variables, by Clairaut's theorem, whatever is there on the right here, they are inverse of each other, right? So let me just note that since they are twice continuously differentiable, by Clairaut's theorem, dou square v by dou x dou y is the same as dou square v by dou y dou x, and therefore and hence we get dou square u by dou x square plus dou square u by dou y square is equal to 0. A similar conclusion can be drawn about the imaginary part of the holomorphic function f. Similarly, by just considering the other derivative, yeah, you just have to consider the y derivative here and the partial derivative with respect to y here and the partial derivative with respect to x here. And by a very similar argument, you can also conclude that v also satisfies a very similar condition. Similarly, dou square v by dou x square plus dou square v. So this is u, this is v, this is u, this is v. I think I am not confusing you with the symbols. Maybe I should be a little more careful. And this is v. This by dou y square is equal to 0. And hence, okay, so let's give this operator dou square by dou x square plus dou square by dou y square some name. So let delta defined to be the operator dou square by dou x square plus dou square by dou y square. Then delta is called the Laplacian operator. And what we just noted is that the Laplacian of u is equal to the Laplacian of v is equal to 0. And therefore, the Laplacian of f is also equal to 0. So we are now in a position to define what harmonic functions are. So let me just define what harmonic functions are. Let u from omega into r be twice continuously differentiable function. We say that u is harmonic if the Laplacian of u vanishes. If Laplacian of u is equal to 0. That should be L, the L should be capital. Right, so we have given a big category or a big class of examples by noting that the real part of holomorphic functions are harmonic, the imaginary part of holomorphic functions are harmonic. So if we are allowed to talk about functions from omega to c being harmonic when the Laplacian of the function f is 0, then we have just noted above that holomorphic function is always harmonic. Now, the converse is not necessarily true. So, examples of harmonic functions are not new. Let me just say that given any holomorphic function, consider the real part of f, consider Re of f and Im of f. All these are examples of harmonic functions. Let's look at one example when a harmonic function is not holomorphic. That can also happen. So a non-example would be, okay, not non-example, consider f of z is equal to z bar. This is a harmonic function. If you notice, the Laplacian of the real and the imaginary part both are 0. So this is certainly a harmonic function. Then f is harmonic, but we have already noted that the Cauchy-Riemann equations are not satisfied anywhere. So there are examples of harmonic functions which are not holomorphic. So this is not a holomorphic function, right? Then f is a harmonic function. So notice that I have just called f to be harmonic. I just mean by this that the real part is harmonic and the imaginary part is harmonic. Then f is a harmonic function which is not holomorphic. So we are dealing with a bigger category of functions here. Harmonicity can be thought of geometrically as the following. After all, the second order derivative is capturing in some sense the convexity of the function. So the fact that the Laplacian is 0 tells us that the convexity in one direction is cancelled by the concavity of the function in the orthogonal direction. So just keep this example in mind. Let u of z be equal to x square minus y square. If you notice, this is the real part of the function f of z is equal to z square, and the convexity along x direction is being cancelled out by the concavity along the y direction. So this is one way of keeping the harmonic functions in your head. Okay, why look into harmonic functions all of a sudden? Harmonic functions have a very interesting property. The interesting property is that given a harmonic function and a compact set in its domain of definition, then the maximum of the harmonic function is always attained on the boundary of the compact set. So to talk about the maximum principle, this is commonly called as the maximum principle. Let me first talk about what is the boundary. So recall that omega contained in X, a metric space, given omega contained in X, the boundary of X, the boundary of omega d omega is given by dou omega rather is equal to omega bar, the closure of omega intersected with x minus omega bar, the closure of the complement. So if you intersect the closure of omega with the closure of the complement, whatever we get is the boundary. So the standard examples are there. If you look at a ball, its boundary is going to be the circle of radius r. So ball of radius r, boundary of the ball of radius r around x naught is just the set of all x such that x in capital X such that the distance of x naught is equal to r. This is exactly going to be the boundary. Let me not spend too much time on this. This is a topological notion which you must be familiar with. Let me now state the maximum principle which I was talking about. So this is the maximum principle for harmonic functions. So recall that harmonic functions are those functions whose Laplacian vanishes. What is the statement of the maximum principle? Let u from omega into r be twice differentiable harmonic function. Let k contained in omega, so this omega is an open subset of C. I generally refrain from, I don't write it, but this is always the case. Omega is an open, let me just put open connected. For the purpose of this proof, I don't think that is needed, but let's put that condition because we are anyway going to study all these things in connected components when we look into it. So let's put this condition of omega being, maybe I'll write it down. Let omega be an open connected subset of C and small u from omega to r be a twice differentiable harmonic function. Okay, let k contained in omega be a compact subset of omega. Then the maximum principle tells us that the supremum of u of z for z in k is the same as the supremum of u of z for z in the boundary of k. not just the supremum, the infimum is also similarly satisfied, and infimum of z in k of u of z is the same as the infimum of z in the boundary of k u of z. So the second statement is a statement very similar to the above, and I'll just remark saying that the second statement follows from the first statement. If we show that the supremum of u of z is attained on the boundary, we have effectively shown this statement as well, because if u is harmonic, so is minus u, and therefore we can talk about the supremum of minus u and conclude things about the infimum as well. So the maximum principle tells us that given a real valued harmonic function and a compact subset k of omega, the maximum, the supremum and the infimum of the harmonic function over the compact set, it is always attained on the boundary. There are points on the boundary where it will be attained. Let's have a look at the proof of this statement. So let's look at the proof. So the first thing to note, we will prove that we shall prove the first statement. We shall prove that the supremum of z in k of u of z is equal to the supremum of u of z in the boundary of k. By considering minus of u, which is also a harmonic function, we can conclude we can conclude the second statement. The second statement follows. Okay, so let's focus on the first statement, which is namely that the supremum is attained on the boundary of the compact. Okay, since k is a compact subset of the complex plane, which is a Hausdorff space, k is a closed set, and therefore the boundary of k is a subset of k. And if you look at the supremum over a smaller set, it has to be less than or equal to the supremum over the bigger set. So we already have the supremum over the boundary of k of u of z is less than or equal to the supremum of u of z over k, because k is a bigger set than the boundary of k. So the only problem comes when this particular inequality is a strict inequality. So let us assume that the inequality is strict and let us arrive at some kind of a contradiction. So assume that the supremum of u of z, where z is in the boundary of k, this is strictly less than the supremum of u of z where z is in k. What does this mean? This means that the supremum is attained in the interior, and because k is a compact set, the supremum is attained at some point. So let z0 be a point in k such that u of z0 is equal to the supremum of u of z where z belongs to the set k. Yeah, this is from a standard result in analysis. Every compact set, a continuous function attains its maximum. So the point z0 is being taken to be one of those points where the supremum is being attained. And we just noted above that the supremum over the entire set k is strictly greater. So that is the assumption we are going by. It's strictly greater than the supremum on the boundary, and therefore z0 is an interior point of k. From calculus, since z0 attains the maximum, we have both the partial derivatives along x square at z0 is less than or equal to 0, and the partial derivative along y square is also less than or equal to 0. But then we do not end up with a contradiction here, because it can happen that the partial derivatives, both of them are equal, and that doesn't contradict harmonicity at least. So this will not at least directly tell us any contradiction. What we will do is we will tweak our function u a bit and arrive at some other contradiction. So to do that, let's first notice that this supremum is strictly less than the supremum over k, and let's call the difference something. Let delta be equal to the supremum of u of z, where z is in k, minus the supremum of u of z, where z is in the boundary of k. And we also know that if you define the function x square plus y square, consider the function x square plus y square. This is a function which is continuous on the compact set K, and hence it attains a maximum. This function is bounded above. Since our set K is compact, let's call the bound to be something, say let's put it as m. We are going to tweak our function u in the following manner. Define u epsilon of z to be equal to u of z plus epsilon times x square plus y square, where epsilon is less than delta by 2 times m. So what does this ensure? This ensures, you should go back and check that the condition of the supremum on the boundary being strictly lesser than the supremum on the entire set is satisfied by u epsilon as well. Supremum of z in the boundary of k of u epsilon of z is less than the supremum of z in k of u epsilon of z. Now we will use the same trick that we just noted above. There will be some point in the interior where the maximum is attained. So let z, now this z will be a different z, let z epsilon be a point in k where u epsilon attains its maximum. Notice that we have just tweaked u a bit. It continues to be a continuous function, and therefore there is a point where the maximum is attained. Again, we are invoking the same property that continuous functions on compact sets attain its maximum. So z epsilon be a point. This z epsilon might be different from the z0. We just know that this inequality is strict, and that means that there is some point. So let's call that point z epsilon. And by a very similar argument above, this is a point where the maximum is attained. Hence, dou u epsilon by dou x square at z epsilon is less than or equal to 0, and dou square u epsilon by dou y square at z epsilon is also less than or equal to 0. We know what u epsilon is explicitly, right? Dou square u epsilon by dou x square plus dou square u epsilon by dou y square. Hence, this should be less than or equal to 0, right? But this is equal to, by linearity of the differentiation, this is going to be dou square u by dou x square, and if you differentiate x square plus y square twice, you get 2. So this is going to be plus 2 epsilon. And similarly, this is going to be dou square u by dou y square plus 2 epsilon. And if you look at the Laplacian of u epsilon at z epsilon, this is going to be equal to the Laplacian of u at z epsilon plus 4 times epsilon. But we know that u is a harmonic function. That was the assumption to begin with. So this is going to be equal to 0. And this tells us that the Laplacian of u epsilon at z epsilon is 4 epsilon, which is greater than 0. But this contradicts this particular observation. because both these are less than or equal to 0. How can the sum be greater than 0? So we have come to a contradiction which contradicts star star. We made some space by multiplying epsilon times x square plus y square to our given function. And therefore our assumption has to be false, which was the assumption here. Therefore this assumption has to be false. Hence the supremum of z in K of u of z is equal to the supremum of z in the boundary of K of u of z. So this is about harmonic functions, real valued harmonic functions. And as a consequence of this, we can also say something about the holomorphic functions. Let's now give a maximum principle for holomorphic functions. So let u contained in, so notice that in the proof above, we did not use the connectedness property to prove that the harmonic functions attain the maximum on the boundary of a compact set. We just used the fact that it was open. Here also we will, maybe we will not be, let me just put the condition that it is open and connected, but for the two results that are being stated, we don't need connectedness in its assumption. And let f from u to c be holomorphic. So as I had noted earlier, in this lecture, when I say holomorphic, I do mean that it is twice continuously differentiable, but we will prove later that holomorphic functions always satisfy that particular condition. So let f from u to c be holomorphic, then the supremum of mod f of z, where then for k contained in omega compact, we have the supremum of z in the set K is the same as the supremum of mod f of z on the boundary of K. So the proof actually follows from one simple observation about the absolute value. Let z be some point in C, then the absolute value of z is going to be equal to the supremum of the real part of z times e to the power I theta, where theta belongs to R. So in some sense what we are doing is, if you are looking at this particular complex number z, then you are rotating it so that it falls on the real axis. So this is, we are trying to capture what this particular line is after a rotation. That's precisely what is happening. So you're getting hold of the supremum over the real part of z e to the power I theta, where theta is varying over R. Alright, so once we have made this observation, now let's get back to the setup we are in. We are interested in proving that the supremum of mod f of z, where z belongs to K, we want to show that this is the same as the supremum of mod f of z, where the supremum is now being taken over the boundary. But then we just noted that this is just the supremum of the absolute value can be written as the supremum over theta in R of the real part of f of z times e to the power I theta. But then this is the supremum over this set can be now written in this manner as well. This is the same as the supremum over theta in R, the supremum over all z in K of the real part of f of z e to the power I theta. Okay, let's define f subscript theta of z, this is being defined as e to the power I theta times f of z. Then f theta is a holomorphic function, right? F theta is holomorphic. And because it is holomorphic, its real part is going to be a harmonic function. And hence, real part of the function f theta is harmonic. And what did we just prove about harmonic functions? We just proved the maximum principle for real valued harmonic functions by the maximum principle for harmonic functions. We have the supremum of the real part of e to the power I theta f of z, where z belongs to k, is the same as the supremum over all the points on the boundary rather now of real part of e to the power I theta times f of z. And let's plug that in here. And what do we have? We then have that supremum of z in k of mod f of z is equal to the supremum over theta in r, supremum of z in boundary of k now instead of k. By this observation, we have just reduced it to studying it over the boundary of k of the real part of e to the power I theta f of z. Now let's do the same trick as earlier by looking at this as by considering the supremum over all theta now. First, we have this is equal to the supremum over all the real part of e to the power I theta times f of z, which is precisely equal to the absolute value of z. And that's precisely what we had set out to prove. So with this, we do get maximum principle for holomorphic functions as well. So we have seen that given a holomorphic function, its real part and its imaginary part, u and v respectively, both turn out to be harmonic functions. Let us now ask a converse question. Given a real valued function u, can we get hold of a v such that u plus iv is a holomorphic function? So that's the next definition given. So harmonic conjugate is the name of such a function. So let u from omega into r be twice differentiable harmonic function. We say that v from omega into r is a harmonic conjugate of u if the function f defined to be u plus iv is holomorphic. And the natural question to ask is, can we get hold of a harmonic conjugate given a harmonic function u? So we will not be answering that question in its generality right now. However, we will prove that when omega is the entire complex plane, we will be able to come up with a harmonic conjugate. And that's going to be the next proposition. Let u from C into R be a harmonic function. Then there exists a harmonic function v from C into R such that V is a harmonic conjugate of U. Not just that, moreover, we can talk about uniqueness of harmonic conjugates up to constants. Moreover, V is determined uniquely up to addition by constants. Let's give a proof of this statement. We will first prove the uniqueness part. The uniqueness tells us that if there are two harmonic conjugates, then their difference is a constant. Let's focus first on one harmonic conjugate. Let V1 be a harmonic conjugate. Remember that this means that V1 and U are tied together by the Cauchy-Riemann equations, because U plus IV1 is a holomorphic function. Suppose V1 is a holomorphic function. Before we use the Cauchy-Riemann equations, let us now use some very fundamental tools from calculus, namely the fundamental theorem of calculus, to rewrite our function V1. Remember that V1 is a twice differentiable function and that it is defined on the entire complex plane. So, if I am to write the following by the fundamental theorem of calculus, both along the x-axis, in the direction of x-axis and in the direction of y-axis, we will be using the one-dimensional version in a slightly disguised form by using the fundamental theorem of calculus. We have V1 of z, let me write z to be x plus iy. So, V1 of z is V1 of 0 plus the integral from 0 to x of along the derivative along the x direction, dou v by dou x of t dt. So, this by the fundamental theorem of calculus will give you V1 of x minus V1 of 0 in some sense. And the second term should be along the y direction. This time, however, it will start from x. So, this is going to be dou V1 by dou y of x plus it dt, where the integrals are from 0 to y. The integral is from 0 to y. So, notice that this one will give us the first form of the fundamental theorem of calculus will tell us that this is V1 of xy minus V1 of x, and the V1 of x will cancel from V1 of x minus V1 of 0 here, and there will be a V1 of 0. Yeah. So, what is left is exactly equal to V1 of x plus iy. This is what we get by using the fundamental theorem of calculus. But then right now is a good time to invoke the Cauchy-Riemann equations, because this is in a different form equal to the integral of what is dou v by dou x. It is going to be equal to the minus of dou u by dou x, sorry, dou y of t dt from 0 to x, because v1 x is equal to minus of uy. And what is going to be v1y? That is going to be equal to ux. So, this is 0 to y dou u by dou x of x plus it dt. We will have a very similar expression for v2. Similarly, v2 of x plus iy is going to be equal to v2 of 0 minus the integral from 0 to x dou u by dou y of t dt plus the integral from 0 to y of dou u by dou x of x plus it dt. The second one is along the y direction. Yeah. And hence, v1 of x plus iy minus v2 of x plus iy, this is just going to be equal to v1 of 0 minus v2 of 0, which is some constant belonging to C. And therefore, you have two different harmonic conjugates to the same function u, the difference should necessarily be a constant. So we have shown the uniqueness part. So notice that this is what we have shown. But we still have not proved anything about the existence. Let's now focus on the existence. We want to show that there is at least one such harmonic conjugate. And to do that, we will use the fact that we did manage to write something about the function in terms of u. So let's use that expression to define what a candidate for v would be. After all, it's only going to define by a constant, right? So define v of x plus iy to be equal to minus of dou u by dou y from 0 to x of t dt plus integral from 0 to y dou u by dou x of x plus it dt. So notice that this explicit expression on the right, it defines a function on the entire complex plane, real valued function on the entire complex plane. In fact, it is differentiable by the fundamental theorem of calculus. The partial derivatives exist. Let us now use the fundamental theorem of calculus again to check whether the Cauchy-Riemann equations are satisfied by the function v. So notice that there are two terms here. The first term is a term which changes along the x direction, and the second one is along the second one is more subtle because there is already an x term. So the first one, however, changes only along the x direction. So if we take the partial derivative along the y direction, then dou v by dou y of x at a point, say x plus it, this will be equal to the first term vanishes, and the second form of the fundamental theorem of calculus tells us that this is exactly equal to dou u by dou x of x plus it. And that's one of the Cauchy-Riemann equations, right, which is one of the expressions in the Cauchy-Riemann equations. Notice that we have still not used the fact that u is harmonic, and that we will be doing when we are studying the derivative along the x direction. Let me just consider it at the point x plus iy. This is going to be equal. So notice that the thing on the right is equal to minus of dou u by dou y at the point x plus the partial derivative along x of this integral. But then our function u is twice differentiable, and by an application of a special version of the Fubini's theorem, we can interchange the limit and the integral and the opera differentiation, and we get this is equal to minus of dou u by dou y at the point x plus integral from 0 to y of dou square u by dou x square of x plus it dt. We also know that u is harmonic. Since u is harmonic, we have integral 0 to y dou square u by dou x square at the point x plus it dt. This is equal to minus of the integral from 0 to y of dou square u by dou y square, because dou square u by dou x square plus dou square u by dou y square is 0. And now we are in an interesting situation. We will now apply fundamental theorem of calculus again, because dou square u by dou y square is the derivative along the y direction, and by applying fundamental theorem of calculus, this is going to be equal to minus of dou u by the first form now, dou u by dou y of x plus iy minus dou u by dou y of x. Yes, we are in good shape because this expression can now be replaced by this expression. And what do we have? This is equal to minus of dou u by dou y. So what is equal? This is basically dou u by dou x, dou v by dou x at x plus iy. That is what we were computing, right, to begin with. I think I made a mistake when I wrote this. This is not dou u by dou x, rather this is dou v by dou x. It looks like the same, but I think here I made a genuine mistake. This is dou v by dou x that we are looking at. So maybe I confused you a bit. So let's go back. Our definition of v is like this. So when we are taking the x derivative here, the fundamental theorem of calculus on this term gives us this term, and we are ending up with this term, right? We will now focus on this term, which is being studied here by interchanging the integral and the derivative, the partial derivative operator, and then we will focus on this particular term. This particular term is being studied here, which by harmonicity of u can be written in this manner, and by using the fundamental theorem of calculus again we can write it like this. So we have used fundamental theorem of calculus quite powerfully in this proof. We are not done yet. So dou v by dou x of x plus iy will be now this particular term. This is equal to minus of dou u by dou y of x plus this term, which is now equal to this term. Let's write that down, which is equal to minus of dou u by dou y at x plus iy plus dou u by dou y at x, and these cancel off, and we are ending up with the second Cauchy-Riemann equation. Hence, u comma v satisfy CR equations. We already started off with a function which has which are twice differential, twice continuously differential, and therefore f equal to u plus iv is holomorphic. So yes, we have proved both. We have proved that if such a harmonic conjugate exists, it is unique. We did prove the existence of one such harmonic conjugate. A similar argument will tell us that harmonic conjugates do exist in many other domains as well, but we will postpone that for a later. In the next lecture, we will study what is known as Mobius functions, which are very important holomorphic functions which are defined on the complex plane. Let me stop this lecture here.